Hello everyone, my name is Jonas Ngnawe. I'm a third year PhD student at the University Laval and Mila-Quebec AI Institute.
We challenged researchers to explain their work across 3 levels of difficulty. First, they'll simplify their research for a young learner. Then, they'll level up to explain it for a student. Finally, they'll dive deep for a fellow researcher.
If I were to explain to my niece, I would say to her, do you know that a phone or a computer can recognize objects, right? So you can give it a picture and it will tell you what it is. It can tell you it's a dog, it can tell you it's a chair, it can tell you maybe it's a cat. Sometimes it can even tell you which dog's breed it is, right? It can tell you it's a Rottweiler or a Bulldog. They are very good at it. So this special program is called an AI, artificial intelligence program. But sometimes they can be wrong for no good reason. For instance, you have a picture of a cat, or you have a cat and you put maybe a special necklace to the cat. It doesn't change that it's a cat, but it will tell you it's a chair or a fridge. That's wrong, right? That's not good. So my work is to help you, or to help the AI to say when it is not confident, when it should have to be careful. So I calculate a number that will help you say, oh, you should be careful. It says it's a dinosaur, but it might not. If you just add a little thing, it will tell you it's something else. So be careful. So in order to do this, to use this number, the program needs to have a special power, superpower, that we call margin consistency. That's special superpower. That's what we introduced, and a lot of these programs that have it, that we studied have it. Some didn't have it, and we showed that even for the networks that didn't have that superpower, we could teach them how to increase that superpower and still help you tell when you should be careful with the decision. You know self-driving cars, right? Self-driving cars detect objects because they drive themselves, so they have to detect objects, they have to detect stop signs and all this kind of thing. But sometimes they are very good, but sometimes they can get it completely wrong. So when you add some small changes that makes no difference to the input. So an image that you add just maybe small dots on it, it will completely say a dog is now a chair or a fridge or something of this kind. And in the case of the self-driving car or something, you might think, oh, saying dog instead of chair is not important. For a self-driving car, if you have a stop sign, the lighting is in a certain way, it will say the stop sign is now a speed limit. So you see that instead of stopping, someone could just go. So it's dangerous. Also, maybe for medical diagnosis or something. So it can be wrong for no good reason, something that would not make difference. So this is dangerous when you use it in sensitive application. My paper proposes a number that you can calculate, just a difference, some A minus B at the end, at the output, that tell you if you should be careful about the decision. It tells you, be careful, a little change can flip the decision. So be careful. So the models for which you can do that are called, have a special property called margin consistency. So we investigated models which resist a bit to this kind of perturbations, and we found out that a lot of them are margin consistent. That means you can use that simple calculation to detect that. But we also found some models that were not margin consistent, didn't have that special property. So we proposed to teach them with another small program beside how they can have this special property or simulate it, so you can still tell if a small change can make the decision wrong. You probably familiar with the image classification task in machine learning. So you know that deep learning models since early 2010 has kind of cracked this task. Like that's the task where deep learning models have been the most successful, surpassing even human performance on that. But soon after, like 10 years ago, it was also discovered that a seminal work that discovered that they are also vulnerable to changes to small, carefully crafted changes to the input space, which are called adversarial examples that you may be familiar or not. So these adversarial examples, they are kind of among other things, are one of the limitations to deploy these models in safety critical systems like transportation, healthcare, and other systems. And so since the discovery, a lot of effort in the community has been to trying to robustify these models to be robust to these perturbations or to detect them. And the robustness to this kind of perturbations is referred to sometimes as local robustness. So it's the invariance. In this case, we specifically define that's the invariance of the decision around a certain epsilon ball around a sample. So if you take samples as values as vectors in the input space, and you have a decision boundary. So if to measure the robustness, you fix a certain threshold, and then you ask yourself if the model is invariant inside this threshold. Normally, if you want to know if a sample, given a model and a sample, if you want to know if the model is robust, locally robust at this sample, you either use an adversarial attack to see if you can cross the decision boundary to know that information, or you use a formal verification methods. And these are expensive computations, like expensive procedures. So it might not be useful if you are in a real-time deployment scenario, or for instance, if you are trying to have big models and you have a large test set, you want to know if the samples are vulnerable. This will take a lot of time. So what we propose is a simple measure at the output of the network, the logit margin, which is the difference between the first logit, the biggest logit, and the second biggest logits. And this difference, we use it as a robustness metric, and we can give you a threshold to detect if a sample is more likely to be attacked or not. So note that we're not detecting if the sample is adversarial. We're detecting if, given a sample, we can easily change the decision. We can easily attack it. So in order to use that, we introduced a property called margin consistency, which is a rank correlation between the input margin, the distance to the decision boundary in the input space, the feature margin, which is the margin in the feature, the distance decision boundary in the feature space. The feature space here is the penultimate layer. So it's a property that says that the neural network is margin consistent if it preserves the order of the samples from the input space to the feature space. The samples that are closer to the decision boundary in the input space are also closer to the decision boundary in the output space. So we show that it's a necessary and sufficient condition to use the logit margin as a proxy score for the input margin, which is the perfect score to detect non-robust samples. So we investigated many models. So note that if you have a model that is adversarially have zero adversarial accuracy, that is vulnerable to all samples that were trained with standard cross entropy, all samples will be vulnerable. So But if you have a model that was a bit robustified with a certain adversarial training technique, some samples will be vulnerable, some samples might not be. So so it's interesting for these models to know which samples are vulnerable or not for this given threshold. So we investigated a lot of these robust models on a benchmark or robust bench, and we found out that a lot of these models are margin consistent indeed, and you can use the logit margin to detect the more vulnerable samples. Just that not all models we found were margin consistent had this high correlation with the input and the output. We found also models that were robust but not margin consistent. For those models, we proposed to learn a pseudo margin from the feature representations using a multilayer perceptron, a small multilayer perceptron, an idea that is inspired by a confidence learning paper from Corbier et al., some paper from 2019. So we learned that pseudo margin from the feature representations, and this new margin is more correlated to the decision input margin than the logit margin. And then you can use now this new margin to detect vulnerable samples.